The Laser Interferometer Gravitational Wave Observatory, first conceived in the 1970s and constructed from 1994 to 2002, is the most sensitive measuring device humanity has ever built. Its twin L-shaped detectors, each with arms stretching 4 kilometers in length, can detect movements smaller than 1/10,000th the width of a proton. That's 10 to the power of -19 meters. A change so infinitesimally small it defies comprehension. But here's the paradox: despite being surrounded by constant vibrations from traffic, earthquakes, ocean waves crashing thousands of miles away, even the thermal jitter of atoms in the mirrors themselves, disturbances billions of times larger than the signals being searched for, LIGO still detected on September 14, 2015, at 5:51 a.m. Eastern Daylight Time, ripples in the fabric of spacetime itself created by two black holes colliding 1.3 billion light-years away. How is it possible to measure something smaller than a proton amid an ocean of noise a billion times stronger? And how did this single detection transform our understanding of reality, space, time, and the very nature of existence itself? The answer reveals one of the most extraordinary scientific achievements in human history, and the beginning of an entirely new way of observing the universe. When physicists Rainer Weiss, Kip Thorne, and Ronald Drever first proposed LIGO in the 1980s, they faced ridicule from much of the scientific community. The idea seemed absurd: build two enormous facilities 1,865 miles apart, each containing vacuum chambers stretching for kilometers, equipped with mirrors so precisely polished they reflected 99.999% of light, all to detect a phenomenon Albert Einstein himself thought would be vanishingly small and impossible to measure. The original mission was straightforward but audacious: prove Einstein's 1916 prediction that accelerating masses create ripples in spacetime, gravitational waves, and directly detect them for the first time. Einstein had predicted these waves would exist, but assumed they'd be far too weak to ever observe. The mathematics was beautiful. The physics was sound. But the engineering challenge bordered on impossible. But there was a window of opportunity. By the 1990s, laser technology, vacuum systems, seismic isolation, and computer processing had advanced just enough to make detection theoretically possible. If LIGO could be built with sufficient sensitivity, and if the universe contained cataclysmic events violent enough to produce measurable waves, the impossible might become real. But here's the counterintuitive detail: LIGO wasn't supposed to succeed on its first run. The initial LIGO detectors, operational from 2002 to 2010, never detected gravitational waves. They were designed as proof of concept, building the infrastructure, developing the techniques, training the researchers. The real science would come from advanced LIGO, a major upgrade scheduled for 2015 that would increase sensitivity tenfold. The original timeline: decades to build the facilities. Years to shake down the systems. Then, maybe, a detection within the first few years of advanced LIGO operations, if they were lucky. Nobody expected success within days of turning on the upgraded detectors. On September 14, 2015, just 2 days after advanced LIGO began its engineering run, 3 days before the official science run was scheduled to start, a signal arrived. At 5:51 a.m. Eastern Daylight Time, both LIGO detectors, separated by 1,865 miles, simultaneously recorded a distinctive pattern, a rising chirp that increased in frequency from 35 Hz to 250 Hz over 0.2 seconds. The signal, later named GW150914, revealed an event of almost incomprehensible violence. Two black holes, one weighing 36 solar masses, the other 29 solar masses, had been spiraling toward each other for perhaps billions of years, gradually losing orbital energy by radiating gravitational waves. In the final moments before collision, they were orbiting each other at half the speed of light, completing one orbit every few milliseconds. When they merged, they released 3 solar masses worth of energy in a fraction of a second, E equals mc squared on a cosmic scale. That's approximately 50 times more luminous than every star in the observable universe combined, but emitted entirely as gravitational waves, not light. An explosion invisible to every telescope, every satellite, every optical instrument humanity has ever built. But LIGO heard it. The detection proved Einstein's prediction. It confirmed that black holes can form binary pairs and merge within the age of the universe. It demonstrated that gravitational waves travel at the speed of light. It showed that space and time are not fixed background structures but dynamic, flexible entities that can literally vibrate. Since that first detection, LIGO has observed hundreds more. On December 26, 2015, just 3 months after the first detection, LIGO detected GW151226, another black hole merger. This signal was subtler, fainter, almost buried in noise, but unmistakable once extracted through matched filtering algorithms. Then came the neutron-star collision on August 17, 2017, GW170817, detected simultaneously by LIGO and its European partner Virgo. This event produced not only gravitational waves but also light across the entire electromagnetic spectrum, allowing telescopes worldwide to observe the source. The combined observation revealed the cosmic furnace where gold, platinum, and heavy elements are forged. By January 2026, LIGO, Virgo, and the Japanese detector Kagra, collectively the LVK network, have catalogued approximately 300 confirmed black hole mergers and counting. During the current fourth observing run, which began in May 2023, the network discovers roughly one merger every 3 days. LIGO's scientific journey can be understood through two parallel paths: what the detectors were designed to find, versus what they actually revealed about the universe. Path 1: Binary black hole mergers. Before LIGO's first detection, astronomers had never observed stellar mass black holes directly merging. They'd found indirect evidence, X-ray binaries where one invisible companion was likely a black hole, orbital decay in pulsar systems, but never witnessed the collision itself. LIGO revealed that binary black hole systems are remarkably common. The masses of detected black holes range from about 7 to over 100 solar masses, with some exhibiting unexpected properties. The first detection alone, GW150914, involved black holes more massive than any previously discovered stellar mass black hole, forcing astrophysicists to reconsider theories of stellar evolution and supernova physics. Path 2: Multi-messenger astronomy. The neutron-star merger GW170817 inaugurated a revolutionary approach to astronomy. Within seconds of LIGO detecting gravitational waves, NASA's Fermi telescope detected a gamma-ray burst from the same direction. Hours later, optical telescopes spotted a new light source, a kilonova, in the galaxy NGC 4993, 130 million light-years away. Over the following days and weeks, every major telescope worldwide observed this single event across every wavelength: radio, infrared, visible light, ultraviolet, X-rays, gamma rays, and gravitational waves. 7 different ways of seeing the same cosmic cataclysm, each revealing different physics. Right now, as of January 2026, LIGO is operating in its fourth observing run with enhanced sensitivity following multiple upgrade cycles. This may not seem like much, just another science campaign in a long-running experiment. But imagine you've spent your entire life reading about the ocean from books, studying maps, analyzing water samples. You understand the chemistry, the biology, the physics. Then one day, someone invents hearing. Suddenly, you can detect waves crashing on distant shores, whales singing thousands of miles away, underwater earthquakes rumbling across ocean basins. That's what gravitational wave astronomy represents for cosmology. For centuries, we studied the universe through light. Now we can hear it through spacetime itself. Before we go further, let's clarify two terms that people often confuse: gravitational waves and gravity waves. Gravitational waves are ripples in the fabric of spacetime caused by accelerating masses, predicted by Einstein's general relativity. They travel at the speed of light and literally stretch and compress space itself as they pass. Think of them like seismic waves traveling through the Earth's crust, except these waves travel through the structure of space and time. They can pass through any material without being blocked or absorbed. Planets, stars, even black holes are transparent to gravitational waves. Gravity waves, on the other hand, are completely different. They're waves in a fluid, like ocean waves or atmospheric waves, influenced by gravity and buoyancy. The name similarity is unfortunate and confusing, but the phenomena are unrelated. So when did LIGO definitively detect spacetime ripples for the first time? The exact moment was September 14, 2015, 9:50 and 45 seconds Universal Time Coordinated, 5:51 and 45 seconds AM Eastern Daylight Time. The signal appeared first at LIGO Livingston in Louisiana, then 7 milliseconds later at LIGO Hanford in Washington. The time delay caused by the gravitational wave traveling at light speed across the 1,865-mile distance between detectors. Scientists knew they'd made a detection because the signal appeared in both detectors simultaneously, accounting for light travel time, matched theoretical predictions from general relativity with extraordinary precision, and had a statistical significance exceeding 5.1 sigma, meaning the probability of it being random noise was less than 1 in 3.5 million. The significance of this milestone cannot be overstated. For the first time, humanity could observe the universe through a medium other than electromagnetic radiation. We could witness phenomena completely invisible to light-based astronomy: colliding black holes, merging neutron stars, potentially even the Big Bang's gravitational wave background. To put this in context, here's a multi-stage timeline of the path to detection. From 1916 when Einstein predicted gravitational waves to 1974 when the first indirect evidence was discovered, earning the Nobel Prize in 1993, took 58 years. From 1974 to 1992 when LIGO was formally founded took 18 years. From LIGO's founding to initial operation in 2002 took 10 years. From initial operation to advanced LIGO upgrade in 2015 took 13 years. From the upgrade to first detection took just 2 days. From first detection to hundreds of detections by 2026 has taken just 10 years. The search for gravitational waves spanned a century. The era of gravitational wave astronomy has barely begun. Here's the core mystery at the heart of LIGO's operation: how does an instrument detect movement smaller than a proton while surrounded by disturbances billions of times larger? Let's start with the measurement technique. Each LIGO detector is an L-shaped Michelson interferometer with 4-kilometer arms. A laser beam is split by a half-silvered mirror, sending half the light down each arm. The beams bounce between mirrors at the ends of each arm multiple times, increasing the effective path length to 1,120 kilometers, then recombine. If the arm lengths are exactly equal, the returning beams interfere destructively. The peaks of one wave align with the troughs of the other, canceling out. The detector registers darkness. But if a gravitational wave passes through, it stretches space in one direction while compressing it perpendicular direction. One arm becomes fractionally longer, the other fractionally shorter. The beams no longer cancel perfectly. Light appears at the detector. The displacement LIGO must measure is 10 to the power of -19 meters, about 1/10,000th the width of a proton. For comparison, if you scaled up the distance between Earth and the nearest star, 4.2 light-years, to the size of the 4-kilometer LIGO arms, you'd be trying to detect a change smaller than the width of a human hair. Now consider the noise environment. Let's use a perspective ladder to understand the challenge. The quietest disturbances LIGO faces are quantum fluctuations, uncertainty in the exact number and position of photons in the laser beam itself. These create noise at roughly 10 to the power of negative 20 meters. The signal must be distinguished from this quantum fog. Thermal noise, the random jitter of atoms in the mirror coatings and suspension fibers, creates vibrations around 10 to the power of negative 18 meters. That's 100 times larger than the quantum noise but still smaller than the gravitational wave signals being sought. Seismic noise, ground vibrations from distant earthquakes, ocean waves, traffic, even people walking near the facility, creates disturbances at 10 to the power of negative 10 meters at low frequencies. That's a billion times larger than gravitational wave signals. When a gravitational wave passes through LIGO, the arms change length by approximately 10 to the power of negative 18 meters for strong signals like GW150914. That's 1,000th the width of a proton. The detectors must measure this while vibrating from seismic noise a billion times stronger, while the mirrors themselves are jittering from thermal noise, while quantum uncertainty adds random fluctuations to every measurement. So how do they do it? The mirrors are massive. Each of LIGO's 4 main mirrors, 2 per arm, 2 per detector, weighs 40 kilograms of ultrapure fused silica glass, polished to atomic-level smoothness. The mass makes them harder to move from random disturbances but still responsive to gravitational waves, which affect everything equally. The mirrors hang from sophisticated multi-stage pendulum systems, quadruple suspensions that isolate them from seismic noise. Imagine suspending a weight from a spring. High-frequency vibrations get dampened. Now hang another spring from the first spring, and another from that. By the 4th stage, vibrations at LIGO's operating frequencies, 10 to 5,000 Hz, are reduced by factors of millions. The vacuum system is extraordinary. Each 4-kilometer arm is a perfect vacuum tube 1 meter in diameter, the longest ultra-high vacuum system ever built. The pressure inside is 10 to the power of negative 9 torr, 1/1,000,000th of atmospheric pressure, preventing air molecules from scattering laser light or transmitting sound vibrations. But the real magic is signal processing. LIGO records data at 16,384 samples per second from hundreds of sensors. Sophisticated algorithms use matched filtering, comparing the data stream to millions of theoretical waveform templates calculated from general relativity, to extract signals buried 100 times deeper in noise than they would be visible. The global network ensures confidence. LIGO operates 2 detectors 1,865 miles apart. Virgo in Italy adds a 3rd detector 5,600 miles from LIGO Hanford. Kagra in Japan provides a 4th perspective. When all detectors see the same signal within light travel time of each other, with waveforms matching theoretical predictions, confidence soars that the signal is real, not an earthquake, not a truck, not a cosmic ray, but actual spacetime ripples from the distant universe. But here's the challenge LIGO faces: the detectors don't run continuously. They require periodic shutdowns for upgrades, maintenance, and sensitivity improvements. When most observatories need upgrades, they schedule downtime but continue basic operations. LIGO can't do that. Improving sensitivity requires replacing major components, installing new lasers, upgrading mirror coatings, enhancing seismic isolation, implementing quantum squeezing techniques. The detectors must be completely offline during these commissioning periods. Between observing runs, LIGO implements upgrade programs funded by the National Science Foundation. The upgrade cycles follow a pattern. After the first successful detection in 2015 to 2016, observing Run 1, LIGO shut down for improvements. Observing Run 2, 2016 to 2017, achieved 25% better sensitivity. Another shutdown. Observing Run 3, 2019 to 2020, improved sensitivity another 30%. The 4th observing run began in May 2023 with further enhancements. Each upgrade brings LIGO closer to its design sensitivity, the theoretical maximum performance achievable with current technology. As of 2026, LIGO operates at approximately 70% of design sensitivity. The remaining improvements will come from quantum enhancement techniques and further vibration isolation. But there's no emotional artifact of shutdown like a spacecraft's final photo. Instead, there's an escalation. Each observing run detects more events than the last. O1 found 3 confirmed gravitational wave events. O2 found 8. O3 found nearly 100. The current O4 run has already catalogued over 200 candidates. Today, LIGO operates with its most sensitive configuration yet. The detectors can see black hole mergers out to approximately 5 billion light-years away, a sphere of space containing hundreds of millions of galaxies. As sensitivity increases, that sphere expands cubically. A 10% sensitivity improvement increases the detection volume by 33%. Current projections suggest LIGO will continue observing runs through at least 2030, with periodic upgrades scheduled between runs. The next major upgrade, A+, is currently being installed during the O4 run using frequency-dependent squeezing and improved coatings. Beyond that, plans exist for LIGO Voyager, a dramatic overhaul using cryogenic mirrors and entirely new optical configurations, potentially operational in the mid-2030s. LIGO's decade of operations has been remarkably successful, but not without crises and challenges. Each time, researchers found creative solutions to maintain sensitivity. In early 2019, LIGO Livingston began experiencing mysterious noise transients, sudden spikes in the data called glitches that mimicked or obscured real gravitational wave signals. These glitches appeared randomly, sometimes dozens per day, reducing the detector's ability to detect faint signals. Why this was critical: glitches can either be mistaken for gravitational waves, false positives, or obscure real events that occur simultaneously, reduced sensitivity. If the glitch rate became too high, the detector would become unusable for science. The automated solution, LIGO's data quality system, uses machine learning to classify glitches in real time, identifying their likely instrumental cause. The algorithm learns to distinguish noise glitches from signal-like glitches by analyzing hundreds of auxiliary sensors throughout the facility. The resolution: engineers traced the problem to electronics in the output mode cleaner, a cavity that filters the laser beam after it exits the interferometer. Small electromagnetic disturbances were coupling into the readout electronics. They installed better shielding and grounding, reducing the glitch rate by 90%. The fix took 3 weeks and allowed O3 to continue with minimal data loss. In 2020, as COVID-19 forced shutdowns worldwide, LIGO faced an unusual problem: how to operate billion-dollar facilities requiring hundreds of on-site staff while maintaining pandemic safety protocols. The detectors couldn't simply be turned off. A full shutdown would require months of recommissioning to restore sensitivity. Engineers spent weeks diagnosing remote operational protocols. They implemented skeleton crews, strict distancing, and remote monitoring systems that allowed essential maintenance while keeping most staff home. The solution required redesigning decades of operational procedures developed around in-person presence. The resolution: LIGO continued operating through much of the pandemic, though with reduced efficiency. Some planned upgrades were delayed, and the O3 run was curtailed earlier than scheduled. But the detectors remained functional, and data quality stayed high enough for science. Looking ahead to the mid-2030s, researchers anticipate a fundamental limit: quantum radiation pressure noise. As laser power increases to improve sensitivity, the photons themselves push on the mirrors with measurable force, creating noise that scales with power. This creates a fundamental trade-off between shot noise, too few photons, and radiation pressure noise, too many photons. The proactive solution, frequency-dependent squeezing, a quantum optical technique that reduces quantum noise at specific frequencies while accepting increased noise at others. By carefully choosing which frequencies to optimize, LIGO can push sensitivity beyond classical limits. The expected extension: with A+ upgrades, LIGO should achieve design sensitivity by 2028 to 2029. With Voyager-class upgrades in the 2030s, sensitivity could improve by another factor of 5 to 10, expanding the detection volume 125 to 1,000 times and revealing gravitational waves from the universe's first black holes formed after the Big Bang. The challenges are ongoing. Each observing run requires balancing detector uptime against upgrade needs. Glitches continue appearing from new instrumental couplings. Environmental factors, logging nearby, construction projects, even hurricanes, create unexpected noise sources requiring constant vigilance. But each observing run, LIGO continues detecting. In January 2026, the LIGO-Virgo-Cagra collaboration announced that the fourth observing run would conclude in 2025, followed by another upgrade period leading to the A+ configuration. The specific end of O4 depends on multiple factors: detector performance, accumulated observation time, and funding availability from the National Science Foundation. Based on current planning, LIGO will continue observing runs indefinitely, with periodic upgrades every few years. Unlike spacecraft that must eventually run out of power or fuel, ground-based detectors can be upgraded and maintained as long as funding continues. The roadmap extends through at least 2040, with discussions of next-generation detectors: Cosmic Explorer in the US, Einstein Telescope in Europe, that would be 10 times larger than LIGO and correspondingly more sensitive. LIGO is not facing a countdown to permanent silence. It's facing an escalation to unprecedented sensitivity. The future of gravitational wave astronomy stretches indefinitely forward. Within the next decade, LIGO and its partner detectors will have cataloged thousands of black hole mergers, dozens of neutron-star collisions, and potentially exotic phenomena we haven't yet imagined: cosmic strings, dark matter events, even gravitational wave backgrounds from the Big Bang itself. The observation network is finite only in the sense that current facilities will eventually be surpassed by next-generation instruments. But the science, the ability to hear spacetime vibrations from across the universe, that connection is permanent. Once established, it will never be lost. LIGO was conceived in the 1970s with a planned detection timeline of decades, if ever. The first facility became operational in 2002 with an expected sensitivity insufficient for detection. Advanced LIGO was designed for a first detection within 3 to 5 years of operation. Instead, detection came within 2 days of turning on the upgraded detectors. Let's compare LIGO's technical specifications to modern equivalents using massive ratios. LIGO's data acquisition system records at 16,384 Hz with 16-bit resolution. A standard 2026 home computer can easily process this data rate. LIGO's computational requirements, once requiring supercomputers, now fit in a desktop workstation. LIGO's laser outputs 200 watts of infrared light. Modern fiber lasers can produce kilowatts in similar packages, 1 out of 10 th the power in January 10 th the size. But LIGO's mirrors, those 40 kg fused silica cylinders polished to atomic smoothness, remain beyond commercial fabrication capability. The precision required to make a surface smooth within a few atoms across a 34 cm diameter cannot be purchased. Each mirror represents months of specialized grinding, polishing, and coating work by expert craftspeople. Here's the paradox: 1970s concepts, 2000s technology, 2015 first light, yet the achievement surpasses anything conceived when LIGO was designed. The first detection involved black holes more massive than theoretically predicted. The neutron-star merger revealed gold formation in quantities exceeding all previous models. Every discovery challenges assumptions, revises theories, and expands understanding. In 2026, LIGO is detecting black hole mergers that occurred billions of years ago in the young universe, when the first generation of stars was forming. The gravitational waves from these ancient collisions have traveled across expanding space for eons, finally arriving at Earth in 2026 to be recorded by mirrors suspended in vacuum chambers in Louisiana and Washington state. And LIGO will continue listening. Through upgrades. Through observing runs. Through the inevitable replacement by next-generation detectors that will hear even fainter whispers from even more distant corners of spacetime. The waves keep coming. We keep listening. And the universe continues revealing its secrets, one ripple at a time.